Okay, so today we'll start talking about MOSFET. So MOSFETs are really the workhorse of the electronics industry, whether digital or power and power conversion industry. Really, MOSFETs are truly a workhorse of this industry. Processors are typically MOSFETs. You typically put in 2 billion MOSFETs on a semiconductor to create today's processors, or even more than that. So MOSFETs are very important. Yeah, so it's a very important device, and it's we're going to build upon the stuff that we learned in diodes. So we still have to understand that current in semiconductor materials is either going to be due to drift or diffusion. Always the case. Okay. In diodes, we realized that diffusion was the main, method of current transfer through a device. That when the device was on, we were actually the current flow was due to the fact that the carriers were diffusing through the barrier, right? So that's when the device was forward biased. Yeah. So the MOSFETs are a bit different, right? So we look at the structure of the MOSFET, figure out how it compares to what we've studied before on the diodes, and hopefully develop an understanding of how to use it in an amplifier application. And like I did with the diodes, it's very critical to remember that DC operating point and then small signal. We will do the same thing here. But with the diode, it was fine. It was not very clear what is the application except for voltage regulation, right? For voltage regulation, it was fine. We have a voltage with ripple. The output was voltage with less ripple, right? So we were sort of attenuating, if you wish, the input ripple by operating the diode at a certain point on the IV curve of the diode, right? But the diode itself is a two-terminal device. It's not, so the current that's flowing is the current that's actually controlling the device, and it's the actual current that is flowing in your load as well, right? So you have a device that is sort of controlled by the external circuitry, and that the current that's flowing inside you don't have too much control over, except very limited small signal control over that, right? But with MOSFETs and BJTs, they are three-terminal devices. So typically we will have two terminals that the current through between these two terminals we will be able to control using the third terminal, right? So you will have these are three-terminal devices, yeah, not two-terminal devices like the diodes, yeah. So, and the basic idea is we're going to be utilizing the voltage between two terminals to control the current through the third terminal. So here, the control signal can be used to cause the current and third terminal to change from 0 to a large value. So you will have a control signal and you will have two terminals, and we will talk more about that. So and there are two types of three-terminal devices. There are MOSFETs and, as I said, BJTs. So MOSFETs is one, and then BJTs, which is the next chapter. So they're called three-terminal devices. So let's say the block here, one terminal, one terminal, one terminal. We will have a control terminal. So this is like a control terminal, and this is sort of a power terminal. So I will utilize this control terminal. Think of it like a valve, where you can choke, like if you have water flowing through this, through this device from due to head, for example. Then with a valve, you can close the valve and open the valve, right? So does closing the valve and open the valve involve the same amount of power you want to transfer water from let's say the ground floor to the 20th floor? No, I typically just push a button, right? That's your control signal, right? And then what happens? Then the motors and the pumps, etc., do their job and push this water to the top or bring this water to the bottom, down, right? So there's a difference between power and control, right? In the diode, it was mixed. It was one device. It was one current and one voltage across the device that was either turning the device on and turning the device off, and it was the same current that's flowing through due to that voltage source, that external voltage source was applied to the diode. So it was not very interesting. We cannot create too much control flexibility, right? If I had a rectifier in the diode application, fine. I was limited to the fact that as soon as this voltage is positive with respect to this, what's going to happen? This diode was going to start conducting. But what if I didn't want that? Because what this gave us was a half-wave rectifier, right? That's what this gave us. But what if I don't want that? What if I want something that looks like this? I cannot do it with the diode. You cannot do it with the diode, right? So because the diode just is controlled by the external circuitry, as soon as I have this voltage applied in my external circuitry, which is this one here, then I'm going to get something fixed, right? So it's not very controllable, right? And that's why from a design perspective, it's called an uncontrolled device. If in a power electronics perspective, it's called an uncontrolled device. 3-terminal devices are all controlled devices. It's like having a switch here. Instead of this diode, you have a switch here that you are actually able to control from an external circuitry using a simple pulse, using an external circuitry, for example, a small pulse. This small pulse will close this gate. This gate, I can have 1,000 amps flowing here, but I don't have to have 1,000 amps, pushing this gate and closing it, right? That's control and power, right? So 3-terminal devices give us this control terminal that we will utilize for interesting applications here. And we'll also utilize as an amp, so we can utilize it as a switch, like I showed here, and we can utilize these 3-terminal devices as amplifiers for your sensor signals. Yeah, we will see how to do that, and it will be based on operating at a certain DC bias point, and then introducing small signal analysis. Same thing we did for the diode, but here it will make a lot of sense because we have this extra control terminal. Okay. So again, as we said, these MOSFETs are the workhorse of today's industry. They're found in analog circuits. They're found in digital circuits. They're found in discrete form. They're found in semiconductor form. So you can cram 2 billion processors, 2 billion MOSFETs on an IC to create a processor, for example. Again, processors operate using ones and zeros, right? It's all digital. And we saw how we can use diodes, for example, to create ones and zeros, a digital format. So we can actually use MOSFETs to do the same thing, and we will look at that down the road, yeah. But the idea is if I'm able to cram as many of those in a small area, I'm able to do many things. I can add ones and zeros, subtract, I can store, all of this extra fancy stuff that we're going to sort of allude to by understanding the MOSFET, yeah. But again, so it can be used for analog and digital, meaning what? I can use it as an amplifier in an analog perspective, or I can use it as a switch. Right? Digital circuits, they will operate on, off, on, off. That's switch type operation. And then amplifier operation is, no, I have a certain gain and a certain attenuation. Right? So MOSFETs can be used for both. Okay, and just from a terminology perspective, it's typically what in the actual device is called an enhancement type MOSFET. This is the most commonly used type of MOSFET, and I will show you what enhancement means. And MOSFET refers to metal oxide semiconductor with field effect transistor. So MOSFET is that's the, if you spell it out, it's metal oxide semiconductor field effect transistor. And we will see what all of these means when we look at the structure of the MOSFET. And there are 2 types of MOSFET based on how you design the material, right? In the diode, we used what? We used P-type material, and we used N-type material, right? So, and we created a PN junction, right? Same thing here with the MOSFET. We will still use the N-type and P-type material. So this doping, all the stuff we talked about for a while, when we talked about semiconductors, even though we didn't really take homework problems, etc. on it, but really the stuff about semiconductors is critical for understanding MOSFET and BJT operation. Yeah. So drift and diffusion is very important. The other thing is, we will take now, P-type material, N-type material, and mix them in certain ways to create a structure. Remember that video that we showed at the very beginning? We will see where this video now is coming from when we talk about this MOSFET and about the MOSFET structure. And then MOSFET structure, there are 2 types of MOSFET. There's an NMOS and there's a PMOS. So it's N meaning N-channel type MOSFET, and then there's a P-channel type MOSFET. So these are the two types that are typically utilized. When you have both on the same silicon wafer, then you have what is called, if you've heard the word before, CMOS technology. So we will talk about that. We have a slide, we have a picture of CMOS technology. But say basically, CMOS technology is when you're mixing, you have a single substrate that has both NMOS and PMOS structures on it. How do you construct NMOS and PMOS structures? We will talk about that in just a minute. Yeah. We will talk about the NMOS in more detail and PMOS in more detail and see how each one is controlled, etc., etc. So let's see. So if we move to device structure, this is how the device looks. So I hope you can relate that to the picture, the video. If you remember the video, basically it was what? Just, it seems like it was just layers on top of layers, right? And this is exactly what we have here. So we have a device that is, if I make it smaller, I don't know if you can see though. Is it clear still? No, not very clear. How can I change the zoom level to zoom in, but I want a specific zoom level. View, zoom to fit. No. View. Zoom selection maybe. No. Here. I want to put both pictures in the same. Yeah. This is, okay. All I'm missing is just a B at the bottom here. I'm only missing a B here. Okay, that's all I'm missing here. Okay, so let's see what this device is made of, and why it's made of stuff like this, and how that is useful here. So first of all, so this is an NMOS. So this is an N-channel MOSFET. So it's an N-channel MOSFET. That's what this is. And the structure is, okay, so you have you get a P-type substrate. So you have a P-type substrate. Remember, substrates or semiconductor materials, again, are constructed from, this single, material that is doped and does not react with anybody else in the environment because of all the covalent bonds. Remember that discussion? So, and that material can be either N-type or P-type, right? So here we will start, and then we get this big ignite, and then you will start chopping it up, and that's called the wafer. Each one of those thin slices is called the wafer. So you start with a P-type substrate or P-type wafer for an NMOS, N-channel type device. Yeah. So you start with this, and then again we didn't discuss how the so you can have this as a P-type or you can have this as an N-type. We didn't discuss how to fuse them together. That is something I'm not an expert on how to fuse the PN junctions together. The device physics guys are able to create the PN junction by bringing the P and N-type material very close to each other and creating chemical reactions that make this this happen. Yeah. Okay. So for now we will just say think of it as, okay, we have a P-type wafer, and then I have also N-type material as well. This N-type material is not part of that substrate. I will add it to the substrate. So I will grow N-type material on this substrate. So I have a P-type substrate, meaning what? Meaning it has majority holes, right? So it has what? It has. Did I put acceptors or donors into the semiconductor to create P-type material? I put acceptors, right? So I put acceptors in there so that any free electrons are bound, right? And then I have silicon is left with some holes that can be filled or used for charge or carrying charge, right? So the majority carriers are the holes. That's the majority. The minority carriers are the electrons, right? In the P-type material, right? And then I bring in, I grow some N-type material on the device, on this substrate. I grow that here, right? And then I add an insulator, so I put some silicon oxide material here. This white material here is a silicon oxide. It's an insulating material that, again, you're able to deposit on the device structure that you've created. And then after that, you put a contact or a metal gate. So you put a piece of metal here, and then you put a piece of metal here, piece of metal here, and a piece of metal here, just so that you can access the device. Okay, so now you've created what? So you've created a gate terminal, you've created a drain terminal, what is called a gate, what is called a drain terminal, what is called a source terminal, and what is called a body terminal here. Again, typically for all practical purposes, we will be connecting the source to the body. So typically when you buy, next time I didn't bring a data sheet for the device this time, but when you buy these devices, it will be a 3-terminal device, not a 4-terminal device, not 1, 2, 3, and 4. It's a 3-terminal device. So typically the source is connected to the body. Okay, so if you look at this structure, let's talk more a little bit about the structure. The structure has a width W. That's interesting that we will be using, and it has this length here is called L. It's called channel region, and we will see why it's called channel region very shortly. So these are the main things from the picture. The length L is about approximately ranging between 0.03 micrometer to 1 micrometer. That's L. W ranges between 0.1 micrometer to 100 micrometers. And we will see how these things affect current flow. Very shortly we will see that, hopefully. What else? And again, the other thing is, if I don't connect this body to the source, the device is symmetric, right? This source and drain is really the same. They're interchangeable. If I don't connect these two together, right? So it's an interchangeable. It's a very symmetric device, easy to construct. Yeah. What else? What do you notice about this similar to diode from ours? Do you see that? Can you see the structure now? Okay, so from this structure, and what we've studied, what can you can you think of something? Try to relate this to what we studied before. No relation? Come on, what we studied before was a p-n junction. This p-n junction was what? A diode, right? So here I have an N and a P. So N and a P together makes a p-n junction. So this is like a diode in this direction. And this is like a diode in this direction. So theoretically, these are like connected to each other, right? It's the same material. So if this is a diode and this is a diode, these are sort of two back-to-back diodes. Do we agree? If it's a p-n junction, it's a back-to-back diode. And then, here what am I doing? I'm placing a short circuit across the source and the body, right? The body is the anode of this diode, and the source is the cathode of this diode, right? So I'm placing a short across it. What does that mean? Am I forward biasing this diode or reverse biasing the diode? How does the diode become forward biased? You have to overcome the depletion layer voltage, right? So how do you do that? By making this voltage, the barrier voltage, smaller by adding an external forward voltage, right? Here, I'm not going to add an external forward voltage, right? So is this diode forward biased? Reverse biased. There's nothing. There's no current will flow in this diode, right? And if I put a positive voltage here at the drain, then I'm also, with respect to the body, then I'm also reverse biasing this diode, right? Correct? Okay. So that's something related to what we've done before. So we see how the adding drain positive voltage will reverse bias this diode, right? We agree? Okay. So now, we said that this is called a MOSFET. and we said that M refers to metal, and this is because of this contact being metal. Again, today it's made of something other than metal, but historically, I mean, it was originally made by metal. Now it's made of another conducting material, right? So, but because it was historically made of metal, the device kept its name. But it's still basically a material that is used to. It's a conducting material like metal that's used to connect the electrical circuit outside to the device, right? So that's why, but it's called metal here. And then this is oxide. Oxide refers to this insulating material. So it's a silicon oxide. It's an insulating material that is deposited on the device. And then S refers to semiconductor. Fine, we have a semiconductor structure. And then the rest is something we will still need to explain. Okay. So now, this is the structure. And let's say I do what? It's also called another name for it. Another name for it on page 234 is insulated gate, IGFET. So insulated gate field effect transistor as well. So field effect we still don't know what it means, but insulated gate means just refers to the fact that the gate is insulated from the device by the silicon oxide material. And we talked about these two back-to-back diodes. So now for the fun. So if I put this at ground potential, right? This source at ground potential. And, fine, we connected these, the body and the source, so we agreed that this diode is reverse biased, right? And let's say I put positive voltage here with respect to ground potential. So with respect to this anode, this metal here is at ground potential, right? So if I put a voltage here, that's positive, and this is ground, right? What did I create? This is an insulating material between them. So I have a potential insulating material and another potential, further away.
An electric field.
An electric field, because I have like a capacitor. Yeah, I have like a capacitor, so I've created something like an electric field. So I've created an electric field due to what? Due to this gate, right? Again, this, capacitors in general. Capacitors do not, consume current, right? As soon as you charge the capacitor, if you have a capacitor across a source, what happens? The source will charge the capacitor, so there will be some current required to charge this capacitor. And then what? And then it becomes an open circuit. So capacitor, this insulated gate is a nice thing because, in steady state, what is my value of current that's at the gate, that's being consumed from my gate here? 0. I charge my capacitor. Let's say I put some positive charge here. And I have negative charge here because this is connected to the negative terminal of the power supply, right? So I've created this electric field that's going to stay, right? Inside the capacitor, if the two plates are charged, the electric field will stay. I mean, it doesn't go away. The electric field will stay there, but you don't have current coming in anymore, which is a very nice characteristic, right? So if this is my control terminal, by design, my control terminal is not going to be consuming current. It's like the infinite input impedance of the op-amp, right? Some current at the beginning just to bias it, if you want to call it, right? And then it's not consuming any current, but it has a voltage across it, right? So there is a voltage at the gate with respect to the source. There is a voltage. I can make this high or I can make it low. So it works very nicely as a control input signal, and then it's going into an infinite input impedance, right? So it's a very nice characteristic that we get with the device. But what does this electric field do? You have this p-type material that has a majority holes and minority electrons. What does an electric field do to the holes? Pushes them down. Right? If it pushes them down, it creates a region called depletion region. Right? So we had a majority holes that are carrying the charge. Like we had before, when we push those away, due to the electric field, what's going to happen? We create a depletion region that is free of these majority carriers, right? And then we're left with the bound negative charges, correct? And then what happens? This electric field is there what is it going to do to the minority carriers, which are electrons in this case? What is it going to do to the electrons? Remember the electric field, if it's like this, and I have a hole, the hole would go with the electric field. How about the electron? Opposite of the electric field, right? So my minority carriers, what's going to happen to them? They're going to go up. I mean, they cannot penetrate the gate. They will go up, and they will, okay, so I had a depletion layer that is now free of the majority carriers. And then I attracted all the minority carriers up. So I created a region here that is full of all the minority carriers. Which are electrons. And I've pushed down all the majority carriers. So I've created what is called a channel. I created that channel in what is called a channel region. Right? So I've created this channel now underneath the insulating material. So did I lose my capacitor? I didn't lose my capacitor. Right? I still have my capacitor in there. And the capacitor, as long as I have a plate with the insulating material, then another plate with a negative charge on it. So if I have a positive charge on top, then the electrons will create a plate here that is negatively charged because of all the electrons. Right? So I've created a plate here. I've created a capacitor at the input. So I still have zero gate current coming in, even though I still have this voltage that is created, that has this electric field created due to this voltage, which pushed the holes down, pushed the electrons up, and created this N channel here. Okay. Now that I have this N channel, what can I do? So far, I've only been talking about the gate to source voltage, and I left this. Let's say I left this initially at ground. All of this was this left at ground. Okay. So now with this left at ground, what I'm doing, what I said is okay. We're okay? With everybody's okay with that? So how about now if I put a positive voltage here with respect to ground? What's going to happen?
The electrons are going to travel.
I have an electric field. Again, a voltage. Since I have a voltage, then I have an electric field. I have voltage here with respect to ground. Right? So there's an electric field here due to the gate to source voltage, right? Right? This black electric field is due to the gate to source voltage, right? Gate to source. Right? G, V, G, S. That created this black electric field. That created this channel. Okay, before I do the drain, for me to actually form this channel, this electric field has to have a certain strength, right? Because first, okay, what does this electric field do? First, it pushed down the majority carriers, created this depletion layer, right? Free of the majority carriers. And then, because I have enough electric field strength to overcome a certain threshold voltage VT, remember the barrier voltage? So because here's something similar, it's called threshold voltage. So because I have enough voltage applied to overcome a certain threshold voltage, I was also able to attract all the minority carriers. Remember, the minority carriers are harder to attract, they're less. Right? So I have to have enough of that voltage to be able to attract the minority carriers to the electrons to the top here to create my channel. Right? So I introduced this threshold voltage concept. Yeah. This channel, so I created this channel. This channel is also called the inversion layer. Inversion, why? Because this is a p-type material, right? The channel we said is what? It's full of what? All the electrons that I brought up. So it's like it's an N-channel material. That's why it's called a NMOS or an N-channel MOSFET. So even though the substrate is a p-type material, because I brought the electrons up and I created a channel, an N channel of negatively charged channel here, then it's called an N-channel MOSFET. Okay? And then I had to make sure that my gate to source voltage was greater than a certain threshold voltage. How much greater? And that is called the overdrive voltage. When you overdrive your car? So it's called an overdrive voltage. So we will introduce overdrive voltage later. Overdrive voltage is basically how much above the gate threshold voltage are you applying. So it's VOV is equal to VGS minus V threshold. Right? So it's how much additional voltage have you applied above the threshold voltage that you need to start creating this channel. Okay? So if I add more overdrive voltage, what does that mean for the channel, from a channel perspective? I'm able to attract more of the minority carriers. If I'm able to attract more of the minority carriers, I can create a thicker channel, right? If you have thicker channel, it's nice because of what? If you have current flowing in a small diameter conductor versus the same current flowing in a large diameter conductor, there will be a voltage drop due to the current flow, right? The resistance is equal to what? Resistivity, length over cross-sectional area, right? So if I'm able, so the resistance and cross-sectional area are inversely proportional. So if I'm able to increase the area of this channel, the width of the channel, which is the area that all the electrons are going to flow through, then I'm able to reduce their resistance, right? So hence, you would expect that if I increase the gate to source voltage considerably above the threshold voltage, I'm able to create a larger channel here, and hence the electrons will have an easier time moving around, right, in this channel. How do they move in this channel? That's the next thing that we're going to talk about. So everybody's okay with the gate to source voltage now? What's the application of that and the threshold voltage and overdrive? Yes?
What is the overdrive? The SVO?
Overdrive is how much gate voltage above threshold voltage are you applying, right? You need to apply a certain gate to source voltage to start initiating this N channel, creation of the N channel. This N channel here did not exist in the P-type material, right? So as soon as you apply the gate to source voltage, what happened? You created this electric field. This electric field pushed the majority carriers down. You ended up with a depletion layer. Depletion means it's depleted of the majority carriers, right? It's just depleted of the majority carriers, which are the holes in a P-type material. And then you increase that voltage further. And then what happens is, to increasing that voltage further, you created a stronger electric field that found the minority carriers, pulled them up, and then they all deposited here in this channel region, forming the N channel.
The voltage that I apply is VOS or
GS, VGS.
VGS?
VGS, the voltage that you're applying. This voltage has a minimum value, V threshold. And then if you increase above threshold, then the threshold is when your channel starts to form. If you increase above threshold, you're pulling more of the minority carriers up, so creating a bigger channel, right? So you want an overdrive. So basically, the overdrive voltage will be the one that really dictates the current flow, because if your gate to source voltage is not beyond the threshold, then you don't have a channel. But as soon as your gate to source voltage is barely above the really equal to or greater than threshold voltage, you have a channel created. Okay, so now I have a bunch of electrons here. What do? I would like current to still nothing is happening. If I don't put any voltage at the drain, nothing is happening. But what if I put a positive voltage at the drain with respect to ground? This is still a voltage with respect to ground. That's going to cause an electric field. Right? This will cause an electric field. This electric field will do what? So this is, again, you have an electric field this way due to the gate to source voltage, right? This was the black electric field. This was due to the gate to source voltage that created the channel, right? And then you have another one. You have another one due to I should have. I'm creating voltage with respect to ground, but also the source is a ground potential as well, right? So I have an electric field that is, can be emanating this way or this way, right? So I have an electric field out of this drain, right? This electric field, if it is, assume now that the vertical component here is neglected because I don't really care to. This is a reverse bias diode, right? So current will not flow out of here into the P region, right? So there is a component of this electric field in this direction, and then there's this is an electric field, let's say, emanating this way out of this drain across the device. So this has a component this way, and a component perpendicular to it, right? Component of the electric field due to this in this direction. This is due to what? Drain to source voltage. So this is a component of the electric field due to the drain to source voltage. There's another component that I will not bother with because I have a reverse bias diode here, right? So I will not care about that. this component of the electric field due to the drain to source voltage, if now I have the channel, so there's another electric field, that is black electric field that was due to the gate to source voltage, right? This black electric field due to the gate to source voltage was in this direction. And this created my channel. Now I add another electric field that is perpendicular to it, right? What is it doing? If you've created your channel and you have your electrons here, right? So you have electrons here. So these are all negatively charged free electrons, right? They are minority carriers that were brought up in this channel. So they concentrated in this channel. What will this electric field do to electrons? They will move in. Electric field will cause drift of electrons. If you have an electron, you have a bunch of electrons here, and you add that were created due to the gate to source voltage, which created this electric field that gave me the depletion layer and brought up these negatively charged electrons, free electrons. These free electrons now, I'm exposing them to another electric field because I applied another voltage here. Initially, I didn't have this voltage. I was connecting this to ground. And then I added a voltage here. If I add this voltage with respect to ground, which is the source, which is the body, source and body are connected to each other, right? So I've added this external electric field now that is going to see these electrons here, right? And they're going to do what? They're going to move against the electric field. The electrons will move against this electric field that was created by this additional drain to source voltage, creating current in the same direction as the electric field. This is my drain current, ID, right? That is going to move here. So this is my drain current through the ground, up through the ground. Do we see how it works? Mariam? Yes? Okay, so it's only because I controlled my gate to source voltage to be a certain value that I created the channel, right? And this control did not really require much current. So I created this channel. I have all these free electrons that have a high mobility. Remember, electrons have a pretty high mobility. As soon as I put this external electric field due to this other voltage that I have, drain to source voltage, then I can have these electrons drift between the drain and source. In which direction? With the electric field.
So the electrons travel from the drain to the source?
Yeah.
Or the electrons travel from the body to the
No, the electrons, first they travel from the body to this channel. Then there's a concentration of free electrons there. If these free electrons, you apply an electric field outside, what's going to happen? These electrons will drift. They will drift in which direction? In the direction opposite to the electric field, and hence creating a current with the electric field.
It's the opposite of the positive terminal.
So the positive is here. The positive terminal is here. So the current will flow out of the positive terminal into the drain, out of the source, and then back into your power supply.
So,
This is the electron. The electrons are flowing the other direction. Sorry. I mean the current. This is current. I'm talking about ID current. The current is flowing in this fashion.
We have voltage in the drain and in the gate.
Here you have, because only when I apply. Because if I don't have voltage between the drain and the ground,
There is
I have to, of course, I have to have a voltage at the gate that is beyond the threshold voltage, right? Because that's what created this whole thing, right? That's what brought all the free electrons to the top.
so the electrons in the body move into the source, and then the drain, the electrons move into the body. Like,
Yes, so the electrons in the body move to the channel. And then, because of another electric field, you made these electrons travel between the drain and the source. They moved from the source to the drain.
is there a possibility that, you can add too many electrons to the body and change the effect of it?
Add 2 electrons to the
Too much.
body.
The drain's applying too much electrons than it originally had.
So you mean the channel becomes thicker?
Yeah, in the source.
Yeah, I mean you want the channel to become as thick as possible, because again, if you have current moving through a certain cross-sectional area, if this cross-sectional area is large, it means that less resistance. You remember, R is rho L over A. If current is moving through through a resistance, it's a resistance. At the end of the day, if current is moving through some material, you can model it as a resistance of some sort, right? If you have a thicker channel full of free electrons, then it's so easy for the electrons to move around, versus a very thin channel, right? So everybody gets how this thing works? Ahmed? Seriously?
So like electrons will keep on moving.
Yeah, electrons will keep moving from source to drain, and then you're depositing more electrons. So then when they come here, so this electron movement is charge, right? This electron movement is charge. Then this charge is basically the electron moving is charge.
It's like conducting.
It's creating the conducting channel. Yeah, the N channel is a channel of a conducting channel, right? So it's conducting because of what? Remember, N-type material by itself is nothing. Is an insulator. So and that's what we had before putting a VDS, right? Before putting VDS, so I put a VGS. I put a gate to source voltage. When I put a gate to source voltage, what happened? I created the channel, pushed the majority holes down, brought the electrons to the top, but still, is anything conducting? Nothing is conducting it. Only when I added an external electric field at between the drain to source, or between the drain to ground, that I did what? That I was able to cause the current, these electrons to move due to drift. Remember, how was our diode working? Due to diffusion. Now this is working due to drift.
Would
Right?
it matter if like we change like
The source and drain.
no
What?
negative
Negative.
on the left on the bottom.
No, no. If you want to put a negative here and here positive, what?
Yeah.
On the source, negative? No, as long as the drain is more positive than the source, it's fine. I will show you some trick now. So
Yeah, on the drain, can you put negative on the left?
on the drain, if it's negative on the left, no. If you're doing that, then you're pushing the electric field in the opposite direction, right? Then the electric field due to the drain to source voltage, E to the drain to source voltage in this direction. Then current will flow in which direction? The opposite direction. It's fine. But remember, you cannot then disconnect the body from the source, because
So it depends on the
you connect the MOSFET by itself, we said, is a symmetric device. So it's a symmetric by itself like that. It's a symmetric device. If I connect the body to the source, it doesn't become symmetric anymore, right?
so I can actually
If you don't connect, if you disconnect this body to the source, you can operate either. You can either operate this is drain, this is source, this is source, this is drain. Does not really matter. Okay, it's a symmetric device. Okay. So because we're going to get something interesting if you try to do that. This diode, we have a section called the body diode. This diode will start doing something interesting in that case, because if you put a negative here, then this is negative. This is the most negative potential in the circuit, and this becomes positive, and this diode can conduct. Right now, if this is a ground and this is a ground, they're connected, this diode is what? Forward biased or reverse biased? Reverse biased. It's in a steady state condition where I have 0 volts across it, then it's not forward biased. So, and here, also when this was grounded, it was also not forward biased. Right? It had basically 0 volts across it. Ground was at 0, the body was at 0, here was at 0, it was not forward biased. And then when I added a positive voltage here, this became more reverse biased. Right? This became more positive here than negative. So this diode became more reverse biased. So now both diodes are reverse biased. Right? You cannot forward bias the diode. If you do that, then you don't have the MOSFET effect. Yes, sir.
What if you go select the breakdown region? Is there a possibility?
Breakdown region. Sure. Yeah, I didn't consider that. But yeah, I'm sure it's a diode. It's a PN junction. So at some point it can break. But do you have gate source voltage or not? I think it's covered later when we talk about the body diode. Let's hold on to that until we talk about the body diode. Let's first operate this device. So operation of this device, everybody's at least okay with it. Do you understand why this gate is merely a control signal? So I think there's a picture with this depletion layer drawn on top and stuff like that. Here, so this is this is what we were talking about. Here's the channel created, but no current flowing yet. Okay, this is the case where my drain to source voltage or drain to ground voltage is still ground. Right, so we went through that. This is the case where I've created the depletion layer, pulled all the minority holes, electrons to the top, and created the channel. Okay, and this channel, as I said, is called an inversion layer. Sometimes, just because I'm inverting the material from a P material, which it was a P material here as a substrate, and then it's converted to N-type material. Right, so that's where this inversion, this word inversion comes from. And everybody is okay with this idea of overvoltage, right? It's the voltage that on the gate, between the gate to source, beyond threshold voltage. So the overvoltage is VGS minus VT, right? It's VT is the threshold voltage required to start creating a channel. The overdrive voltage is the voltage now, the threshold voltage required to create the depletion layer. If I want to create the channel, I have to have the VGS, the gate to source voltage, be at least threshold voltage. Yes, sir. It's always what? VT depends on the material. It's a material characteristic. Yeah. It will have a value. We'll talk about the value of VT later. Yeah. But it will have a certain threshold voltage depending on the material itself and the construction of the device. Yeah. Okay. But it's a voltage. It's a fixed value for a material. Okay. So any questions on this? We're okay? Yes, ma'am. V overdrive voltage, VOV. It's the amount of voltage beyond the threshold voltage that you're applying between gate and source. Right? To create the channel, you need to create the channel. Before creating a channel, you create a depletion layer. You deplete the region from the majority carriers, and then you pull the minority carriers to the top. Pulling the minority carriers to the top will not happen until you have put a gate to source voltage that is at least equal to VT. Anything you put above VT is extra. Extra, what does it do? It pulls more of the minority carriers to the top, creating a thicker channel. Why is a thicker channel more interesting? Because you have more charges in there. If you have more charges in there, then you can move more charge. Move more charge means you can move more current. Right? If you have more charge that you can move, then you can have higher current. Okay? Okay, so that's being the case. So, just before we move on, do you see now where the name field effect transistor comes from? So, metal oxide semiconductor. Field effect is due to these electric fields that I'm applying that are the reason to cause the current to flow. Right? Field effect transistor. Okay? So it's the field, this external field, due to the voltage applied between the drain and the source, or the drain and ground, because source is at ground potential, for example, in this case. It's the voltage between. In general, it does not have to be at ground potential, okay? But it's the voltage between, the VDS voltage that I'm applying, voltage between drain and source that I'm applying, is going to cause this field effect to cause the current to flow. Okay, so that's where this FET word comes from. Okay, so now we explained all the acronym. Okay, now let's sort of formalize what we're talking about into a set of equations. And again, the objective is what, guys? The objective is to figure out, I've created this gate to source voltage. We said that the gate to source voltage will have a value, but the current is what? Almost zero, right? Because it's a capacitor. I will charge it to a voltage, and that's it. There is no current being consumed. Right, so the current will flow between the drain and source, depending on the width of the channel and how much voltage I'm applying. Correct? So that's what we need to formalize, and the objective is to do what? The objective is to figure out how much current is flowing when my gate to source voltage is a certain value. Right? This is my control variable, right? Isn't this control variable what's controlling how much minority charges are created and pushed to the N channel? So it's this control voltage that is pushing the minority carriers to the channel. I create a larger VGS, I have a larger channel. Means I have more free electrons to push current. And this is only control. And then you want to actually have this current to flow by applying this VDS, right? That's the VDS will actually what will cause the current to flow. But how much current flows is really controlled by VGS. Because it will depend on the thickness of the channel that you've created. Yeah.
You said VDS. What does that do again?
VDS is what's caused the drift. The actual current flow will be initiated by VDS, right? But how much current will flow? Is it really dependent on VDS? No, it will depend on how much electrons you've actually been able to put in the channel, right? So that's why this is my control terminal, and this will be my power terminal, right? The power terminal will have the current flowing. How much current will depend on VGS, okay? So now let's look at the equation. So again, the equations it's sort of gonna come from, we will not derive the exact physics, but it has to make some sense, right? So the equations, okay, so we said that this overdrive voltage, or they call it the effective voltage, is basically the gate to source voltage minus this threshold. How much above the gate to source voltage are you applying? How much voltage above the gate source voltage are you applying? Because that's going to control the thickness of my channel. Because it controls the thickness of my channel, that means it controls how much charge is in that channel. So obviously the equation for charge will be directly proportional to the overdrive voltage. So how much charge is in that channel will depend on your capacitor size that you formed. Remember, what is a capacitor? Capacitor analogy is like a bucket of water, right? That's the capacitor, as an analogy, right? When you fill it with water, the level of water is the voltage. Okay? Think of it that way. If you have a bucket of water, and let's say you have a small bucket of water, and you want to fill it up, how much water do you need to fill it up to a certain level? Small bucket. Small amount of charge. Small amount of charge will fill the capacitor up with voltage very quickly, right? Versus a large bucket of water. To get to the same level of voltage, you have to put a lot of charge, right? So hence, the amount of charge is directly proportional to this capacitance. So you've created the capacitance. How did you create it? COX is this capacitance that was created due to the silicon oxide layer. COX is because of the silicon oxide. OX stands for the oxide, right? So C is the capacitance that you've created. Remember, we had a metal on top of silicon oxide, metal that has positive charge due to the gate to source voltage was positive, for example, and then we had an N channel created here, right? So this is a capacitor. This is a capacitor. This capacitor size depends on dimensions of this capacitor. We will have the equation for, I think that you took the equation for that in 322, right? It will depend on the area of the plate and the dielectric material you have between them, between the two plates, right? That's the value of the capacitance, right? And it will dictate how much charge can be deposited on the capacitor, right, that you've created. And that's why charge is directly proportional to this COX. Right, the capacitor that you've constructed. You've constructed this capacitor by putting a certain width of silicon oxide material beneath the metal conductor. Yeah. Okay, and then what? So you have this capacitor, and then you've created a channel. So this CX is okay, this is okay, right? WL now is what? W is the width of the channel. W is the width of the device, right? Width of my device, and L was the length of my channel. Exactly, so area. So you have a certain thickness and then cross-sectional area. Thickness was created by the electric field. Thickness of the channel was created by the electric field, gate to source electric field, right? And then that has a cross-sectional area. The current will flow through that cross-sectional area, right? So it's obviously that this charge will be proportional to that area as well. Right? So everybody's okay with this? So if I have charge, I can calculate current. Right? And that's our objective, actually. So before we get there, we'll talk more. Okay, so we said this capacitor depends on, you've constructed this capacitor. This capacitor depends on the permittivity of the material, permittivity of the dielectric, and the distance between, if you remember 322, it's the permittivity of the dielectric over the distance, the thickness of the dielectric. Thickness of the dielectric depends on what? On your process, technology. Remember, that video we saw in the first class. All these things on top of each other, right? The thickness is what? If you want to create a big capacitor, what do you want TOX to be? Small or big? Small. Do you want to create a big capacitor or no? We want, because if you have big capacitance, then charge can be a lot. You can have a lot of charge stored in there, right? So, and that you can do by creating a very small thickness of that capacitor.
So the larger the gap between the plates, the bigger the capacitance, the electric.
The oxide thickness. So the oxide thickness is TOX. This oxide thickness has a certain permittivity. The capacitance depend on the permittivity, the material, dielectric material, and the thickness of that oxide material. If I make this small, I can make the capacitance big. Right? How do you make this small? This depends on the process, technology. If you get into microelectronics, people are trying to, if you heard of Moore's law, where the idea of ever shrinking size of semiconductor material. So you can put, first we were able to put 1 billion devices, 1 billion MOSFETs on a chip. Now we can put 2 billion. Then we can put 3 billion. How is that happening? That is happening because you're able to make smaller and smaller features, manufacture smaller and smaller features. Hence, you're able to operate devices. You still want a certain amount of current to operate a device, for example, right? But now you can store more charge in a smaller device, right? Means what? Means you can cram more of these devices and do more things, right? That's what this means. So COX is the device parameter, is a manufacturing dependent or a process dependent parameter, and of course, then this COX times the area, so this capacitance times the area will be a good indication of the total capacitance, right? This is the total capacitance that you can store charge in, right? So you have a capacitor, and then this capacitor also has a cross-section area, right? So that's this COX times WL sort of term that we have here. So all of this is, okay, just we're trying to see how much charge I'm storing, right? All of this is, basically it's this equation, but I'm going to take COX times WL and just term it, combine it into, this capacitance also has a cross-sectional area. That's really what they're saying here, yeah. Because capacitance depends on the thickness and cross-sectional area. So they've put all of those together, and they're telling us that this is a process-dependent parameter. Okay, it makes sense, a lot of sense that it's a process-dependent parameter. Yeah. Okay, since it's a process-dependent parameter, let's continue. Okay, so now we've figured out how much charge we can store, right? Now we said we can also apply now the drain to source voltage. We already applied it. I explained how to apply the drain to source voltage, and that's going to cause the current, the charge to drift, right? So we already calculated how much charge. If I now take this charge that I got from this equation and divide it by unit length. So if I take the charge that we had from original equation, I divide it by L, right? I removed the L from here, right? I kept the W, but I divided by L. So this is the amount of charge per unit length of channel, right? So if I take that amount of charge per unit length of channel, apply an electric field per unit length, which is this electric field per unit length is this term here. This will mean I have a certain electric field on a unit length. This electric field on a unit length of charge will cause this charge to move. Due to what? Mobility. Remember the mobility due to the electric field? That's what we discussed before. So this movement now, due to mobility, is what's going to cause current. So now current is equal to what? Current is equal to the mobility times COX, this capacitance that we created, times W divided by L, because this capacitance and mobility we calculated per unit length, right? And then multiplied by the overdrive voltage, and then all of that was due to the fact that now I've applied my external electric field, which was due to VDS, right? The electric field that caused drift was due to addition of VDS, right? So all of that now, everything we took, all the previous equations, I combine, and I have an equation for current. This
Yeah.
current,
And it's the current traveling through the channel.
that's the current now that's traveling through this channel. Okay, so that's the current that's now traveling through this channel. They rewrite V over drive in terms of VGS minus VT. That's fine. And now what do we have? We have something interesting. We have, this is, remember Ohm's law is what? V equals I times R. So here I have what? I is equal to something times V. So it's like 1 over R, right? It's V over R. This is what? 1 over R, or the conductance of the channel, right? So this is the conductance of the channel. So the conductance of the channel, the ability of the channel to conduct the current, is now something that I have here. And it depends on what? My overdrive voltage. My overdrive voltage is basically the gate to source voltage, right? So my conductance of my channel, which is, it makes sense, right? We said that, you know, if I have large gate to source voltage, I'm able to cram more of the minority carriers, and I'm better able to conduct current, right? So that I have a conductance that is dependent on my gate to source voltage here. Everybody's okay until now? We're good? Okay, so let's see what's next. So we now read, you know, again, we do some more term reorganization. So this mu times Cx, we call it process transconductance parameter. Again, because it's a process parameter, we will take it out and call it process transconductance. We just want to simplify the equation. I'm not going to introduce anything new. Basically, this is my current. This is really my current. Okay, I'm just going to try to reorder the terms and give them some names and simplify the shape of the equation. Okay, so I will take this mu times Cx and call it the process transconductance parameter, and you know, W over L is my aspect ratio. Let's see. So I will take my, again, W over L is what? Is also a process dependent parameter, right? Because I would like, the W over L is going to define how much current is flowing. You agree? So if I want more current to flow, what do I do to W over L? More current to flow. Make L as small as possible. Make small L, right? If I do this, I want to make L small. L small means what? It's a process dependent parameter as well, right? This length of my channel, I want the length of my channel to be small, right? This length is small. How do you decrease the length of the channel? Then it depends on the process limitation. Is the process limited or not? Right? So all of these are process dependent parameters. So they sort of group all of these process dependent parameters. So they group the first ones, which were obvious and we talked about before: mobility of the semiconductor, mobility of the electrons, multiplied by the capacitance, the oxide capacitance. This we found was process dependent. And then we found that the aspect ratio W over L affects current flow. And we also found that this is process dependent. I want to make L as small as possible. Fine. But there's a limit on that. Actually, multiple limits on that. One is the process, and one is what we are actually trying to achieve. If you make such a small channel, right, then theoretically you need to make the channel very wide if you want to push the same amount of charge, right? So, which is the W over L factor. Right? So, but we will see that the electric field that you add at the drain size, on the drain side, will really limit how small you can make this L. So anyway, so we group all of these together still, okay? After we group them together under this term Kn, they go back and expand them again. So they go back and expand them again. So this, again, Rd is 1 over G. Rd, the resistance of the drain to source, is 1 over the conductance of the drain to source. And what we have here is an equation that says what? That the resistance, the drain to source resistance, which is the inverse of the drain to source conductance, is dependent on the gate to source voltage, inversely proportional to the gate to source voltage. Right? What does this mean? That if I do what? If I increase the gate to source voltage, I have less drain to source resistance. That's basically what this means, yeah, right? Which is nice or bad? Remember, your current is flowing between your drain and source, if you have an equivalent resistance between the drain to source that is low, it's good for you, right? That's a good thing, yeah. And the other thing is, we found that this conductance, or 1 over the resistance, also depends on, yes, we found that this depends on VGS. So we found that the resistance that we have depends on the gate to source voltage. And that the relationship between the value of ID is governed by this resistance. Right? It's like having what? It's like having ID, current flow, from a voltage source, VDS, with a resistance between them that you're controlling. Right? You're controlling the value of the resistance between the drain to source. Just think of it simplistically as you have drain current and source voltage flowing. This is your VDS voltage that you applied later. Right? First we had VGS. VGS is what's controlling this value of resistance. Right? It's like having something like this, RDS. Can you imagine this? So this is something you're controlling by the value of VGS. So I'm applying a VGS to create a resistance of some sort.
Is that the resistance in the channel?
Yes, that's the resistance in the channel that we just hear. It's with what's relating ID and VDS. So you're relating, you have a resistance that you are controlling that is going to be in the flow of current ID that you are basically consuming, or from your power supply DS, VDS. You see what's happening? So this is good or bad. If I next class we'll see that if I fix the value of resistance, if this value of resistance is fixed, how would I draw the relationship between I and V? If this value of resistance is fixed, 5 ohms, it's a straight line, right? I versus V is a straight line. This is the slope of this line is delta I over delta V, which is 1 over R, which is this value here, right? And that's what we have on the next slide here. So remember, different values of VGS will control the value of R. So different values of VGS will control the slope of this line. And where you are on this line will depend on the value of VD and ID that you have. Okay, so we'll stop here and we'll continue with the rest of the parameters later. Yes, ma'am. Huh?
Have the exam